afternoon, my dear students. My name is Dr. K.C. Apparao, working as an associate professor in Mechanical Department, Institute of Aeronautical Engineering, Hyderabad. Okay, in previous classes, we discussed the rate of heat transfer through conduction process or conduction mode. Now, we'll see the heat transfer through convection mode. So, you know that conduction takes place in only in solids. Convection takes place from solid to fluid or fluid to fluid. You know that. So, we already know that there are three modes for the heat transfer. First one is the conduction, next one is the convection. So, third one is the radiation. So, conduction topics has been covered in previous classes. Now we'll see the convection process. So, rate of heat transfer through convection. Okay, you know that in conduction, so heat transfer takes place by two phenomena. One is the lattice vibration, another one is the free electron movements. But in convection, it means in conduction there is no bulk motion of the or bulk movement of the particles. But in convection, convection is completely associated with the bulk motion of the or bulk movement of the particles. Okay, so particles moves from one place to another place. Movement of particles should be needed to convert the to transfer the heat from one body to another body here. Okay, so you know that so PV is equal to nRT formula. Okay, so it means next P is equal to N by V. RT also you can write like this. Okay, so just N by V is nothing but density, you know that. Okay, so density is equal to RT by pressure P by RT. So this is the formula. Okay, so here density is indirectly proportional to 1 by T. If the temperature increases, automatically density of the fluid will be decreases. So you know that that principle. So if the temperature increases, so if the density increases, temperature will be decreases. If the temperature increases, density will be decreases. So the both are in direct proportion to each other. Okay, so suppose we will take one example here. So this is a container. So heating on any stove. So initially you know that the bottom surface of the just this vessel will be heated through conduction. So you know that after that the fluid layers or fluid particles which are very near to this bottom layer of the vessel. So those particles will be heated so through convection method. Okay. So next to the particles which are heated, those particles density will be decreases. So when the density of those particles decreases, it means less density particles comes to upward direction, heavy density particles comes into downward direction. So it means heat transfer takes place from bottom to upward. So by the movement of the particles from bottom to top, because these particles moves from bottom to top because of density differences. So less density particles comes into upward direction, heavy density particles, so less density particle comes into upward direction, heavy density particles moves into downward direction, like this one. So this is called buoyancy effect, you know that. So it occurs so naturally. So this type of convection is simply called as the natural convection. So because it occurs naturally, because when they heated the particles density will be decreases. Those less density particles moves into upward direction, heavy density particles moves into downward direction. When the particles moves from one place to another place, automatically the heat transfer rate of heat will be transferred from bottom to topward. It means so the rate of heat transfer takes place from the bottom surface to throughout the fluids. So this is occurred by the uh, naturally by the effect of buoyancy. So this type of convection is called as the natural convection. Okay. With the bulk movement of the particles, here we can see heavy dense, less dense particles, heated particles move in upward direction. Heavy dense particles moves into downward direction. Okay, so that is the natural convection. So another one is the forced convection. Here, bulk movement of the particles is displaced or moved from one place to another place by the effect of some external agent, some external agent like fan and something. So here the particles moves from this place to this place. It means the fluid particles moves on the hot surface. So from one place to another place by the help of some external agent. So here heat transfer takes place from one place to hot body to fluid by the effect of the some external agent. So that is called that one is called forced convection. So totally convection is two types. One is the natural convection, another one is the forced convection. Natural convection occurs by effect of the buoyancy, so by the effect of density differences. But forced convection occurs by the effect of some external agents like fans and some blowers like this one. So these are the types of convections. Okay. Now we'll see the convection. You know that convection. So the mathematical formula for the convection is given by Newton's law. Newton. So according to Newton's law, we know that heat flux or rate of heat transfer is equal to HA into Ts minus T infinity. So Ts is the temperature of the hot body, solid body. T infinity is the atmospheric air temperature or fluid temperature, anything. So H is the rate of heat transfer of the fluid. A is the area of the surface. So you can rewrite like this one: Q by A is equal to H into Ts minus T infinity. So Q by A is nothing but heat flux. You know that. So here, just like you can say, simply say that the rate of convection heat transfer. So heat transfer, Q convection, small q convection expressed in the units, you know that watt per meter square. So this is the flux. It proportional to the one is proportional to Q by A is directly proportional to temperature difference Ts minus T infinity. Another one is the Q by A is directly proportional to H, rate of heat transfer. Okay, so that is the proportionality constant. Okay. You know that this is the formula. So but finding H for the different fluids is very important. So because fluid properties depend upon so many parameters, properties like density and viscosity and kinematic viscosity and Prandtl number. So those are the so many parameters are there. So by using those parameters, you have to find the rate of heat transfer for the particular fluid. Okay, so that is very important in this chapter. Okay, we'll see. So next mechanism of the, first of all we will see the forced convection. So forced convection, it means flowing of or moving of the fluid on a solid surface, okay, by some external agent like through forced convection. So first of all we will see the forced convection. So the mechanism of the forced convection we will see, and so we will see some numericals based upon the forced convection. So after that we will see the mechanism of the natural convection and flow in any pipe and something. So by naturally we will see that we will see the mechanism of natural convection. We will see the different numericals based upon the natural convection also. First of all, initially we will see the mechanism of the forced convection. So here just like you know that there is a solid surface like this one. So fluid is flowing like this one. Okay, velocity of the fluid is equal to u alpha because it is the forced convection. So by the help of the some fan or some external agent, so the fluid will move from one place to another place. So the fluid should have the velocity. If the velocity is constant, means that is a flow, forced convection. Okay, so so this is the fluid is flowing like this one. Then we know that the velocity profile of this one is equal to is like this one. So at the at the so this is the solid surface, you know that solid surface. Okay, so the layer of the fluids which is very near to solid surface, here the movement of particles are very less. Okay, initially the movement of the particles, it means velocity of the fluid will be increases gradually at particular point. So this velocity is very near or very are equal to just like so this fluid velocity, it means u alpha, that is not equal, very near to that one, it means 99 percentage of u alpha or 0.09 into u alpha. Okay, so this is the velocity profile, you know that in y direction, here you can see. Okay, so this is the solid surface. So Ks is the thermal conductivity of the solid surface. Okay, so you know that heat transfer takes place in the solid, so by conduction process, you know the rate of heat transfer for the solid surface, that is the that one is the q conduction is equal to minus Ks into area into dt by dy. So okay, this is the solid one. Okay, but in case of convection also takes place through Fourier's law, because the layer which is very near to the solid surface, there is just like there is no movement of the particles, it means that layer those particles layer act as a just like small solid surface. So then you can take this formula q conduction through that fluid. So that fluid, it means the layer of the fluids which is very near to this solid surface. So we can read it like this one, this is equal to q conduction for the fluid equal to kf, thermal conductivity of the fluid is very less, but you have to consider this one. So kf into area of the solid surface into dt by dy into solid fluid. Okay, so it means in this case heat transfer takes place. First of all, heat transfer through solid body by conduction. Next to heat transfer to solid to liquid, which is the layer of the liquid which is very near to solid surface, but the layer of this fluid, layer of the fluid act as a solid because there is no movement of the particles. So it means here also conduction heat transfer takes place from the initially heat transfer takes place from the solid to fluid by conduction process, small amount, that is the kf into area into dt by dy. Then so from fluid to fluid, so that takes place by heat transfer takes place by convection principle. So in this way, just like heat transfer takes place. Okay, so this is the forced convection mechanism, you will see. Now we'll see the just like thermal boundary layers, we will see. Okay, so thermal boundary layers in forced convection, and just like hydraulic boundary layer and thermal boundary layer in forced convection, and hydraulic and thermal boundary layers in natural convection, both of them we'll see. So initially we'll see the, so with respect to forced convection, so hydrodynamic boundary layer. Okay, velocity boundary layer we can call it. Okay, so velocity boundary layer, hydrodynamic boundary layer. So we'll see. So this is the hydrodynamic boundary layer. Okay, so we'll see, first of all we'll take heated solid surface. The fluid is flows on the heated solid surface. The temperature of the solid surface is equal to Ts, you can see. Okay, so fluid temperature is equal to T infinity, you can take. Velocity of this fluid, so u alpha, so you can take So this is the velocity. So this is the, just like here we can take, this is the length of the solid surface. This is one is the initial point, is the ending point. Here x is equal to 0. Here something x is equal to some value. So here x is equal to L. So x is equal to 0. We can call it so leading edge. This is the leading edge. So x is equal to L. We can call it as a trailing edge. Trailing edge. Okay, we'll see the boundary layer thickness, velocity boundary layer thickness. Okay, it is represented by delta. Okay, so here, so this is the velocity profile. You know that velocity profile. Initially, this particle does not have velocity, which particles are very near to solid surface. Next, gradually the velocity of the fluid increases. Okay, so here we'll see the so local velocity. This local velocity, it gradually increases. So just at particular point. So after that one, that same value will continue it. Okay, so this is the point where this velocity, this local velocity is very near to stream velocity. So that value, so local velocity, here this velocity is very near to stream velocity. So not equal to stream velocity, but very near to stream velocity. It means so 99% is of stream velocity. It means, so here the velocity is equal to 0.99 u alpha. So it means stream velocity. It means very near 99%. So here you can do. So at that point, the distance from the solid surface to that point, so that is called as the velocity boundary layer. So that is simply called as velocity boundary layer. Here just a definition has been given. Boundary layer thickness or velocity boundary layer thickness. So delta is defined as the boundary layer thickness. So is defined as the distance from the surface of the body, this distance to the point. This is the point where the local velocity. So this is the velocity, local velocity is reaches to the 99% of stream velocity u alpha. It means the increased velocity, this local velocity very near to stream velocity, but not equal, but very near. So it means 99% reaches to 99% of the stream velocity. Okay. So that distance that is simply represented by delta. So that is called boundary layer thickness. Boundary layer thickness. So this is the layer of the velocity boundary layer, hydrodynamic boundary layer. So this is the boundary layer thickness. Okay, this is the profile in forced convection mechanism. Okay, so similar way we will see the. Okay, so in this one we will see few parameters. You know that in the velocity profile, viscosity is very important parameter. So the opposing force between the two layers, you know that frictional force, the friction between the two adjacent layers, these, so some type of adjacent layers act similar to drag force. It means frictional force. You can find the drag force. Okay, so it is represented by FD. Sometimes it will be asked in questions, so you have to learn about this one. Okay, you know that this is the shear stress tau is equal to, that is the formula. According to this one, you already learned in fluid mechanics. So tau is equal to minus mu into du by dy. So this is the formula. Okay, so next this tau is equal to shear stress is at a particular distance x is equal to, you know that, minus mu du by dy. So you can write like this one. So this is the equal to cfx it is the drag coefficient Cfx into half into density rho into velocity square. So this is the formula. So this is the formula for the shear stress. You already learned in uh, fluid mechanics. Okay, you know the formula also. So drag force is equal to shear stress into area of the solid surface. So you know that too. So that is the Fd is equal to tau x into A is equal to Cfx drag force coefficient into half rho u alpha square into area. So this is the formula. You have to remember that one, because in some questions just like so you have to find the drag force. So drag force will be asked. So the drag force per unit area is called as the shear stress. You know that one. Okay, so you know that in the flowing of the fluid, two types of flows we will see. Okay, so here just like two types means laminar flow we can observe, turbulent flow we can observe. Okay, so in between flows means transient flow. Okay, so you already learned in fluid mechanics. So there are types of the flows. One is the laminar flow, another one is the turbulent flow. So just like in medium it means transient region. So some particles in follows laminar flow, some particles are in turbulent flow direction. So here you can observe. So this is the same forced through forced convection. The fluid is flowing on the solid surface like this one. So you know that this is the velocity profile. It means at this point that is the delta. Here also at this point that is the delta. Okay, so you know that laminar flow, the fluid particles are very parallel to each other. Okay, in a uniform direction fluid particles move. So in turbulent direction, so turbulent flow particles move, direction is so zigzagging position. So mixed with each other, mixed with each other. So you know that already learned what is laminar flow and the turbulent flow. So up to this area, this portion we can call it the laminar boundary layer. Okay, so this is the transient boundary layer we can observe. So after that this is the turbulent boundary layer. Okay, so to identify the flow, so you know that it is identified based upon the Reynolds number. You already learned in fluid mechanics. You know the basics. Okay, so based upon the Reynolds number value, we can identify which type of flow. Either it is laminar flow or a turbulent flow. Okay, so you know that Reynolds number. So the formula for the Reynolds number is equal to, you know that is the inertia force by viscous force. You know that rho velocity L is the length of the solid surface by mu. You can rewrite like this one is equal to velocity into length by mu by rho. Mu by rho is nothing but mu. So that is the kinematic viscosity. So in case of solid surface, you will take the length. In case of just like circular pipes, you can take the diameter ud by mu. This is the Reynolds number formula. Use the velocity of the fluid stream velocity, and so L is the length of the solid surface. In case of pipes, the diameter of the pipe. Mu is the just like property of the fluid, that is the kinematic viscosity of the fluid. Otherwise you can write like mu by rho. So dynamic viscosity by density of the fluid. Okay. So based upon this Reynolds number you can identify. So there is a one critical value of the Reynolds number. We can call the critical Reynolds number. That is the critical Reynolds number. So less than the Reynolds number is less than the critical Reynolds number, that is called so that shows the laminar flow. If the value of the Reynolds number is greater than the critical Reynolds number, that flows that flows, it means greater than RE is greater than the critical radius number. So that shows the turbulent flow. So based upon the Reynolds number, we can identify each type of flow. So the value less than critical Reynolds number, that is laminar flow. Greater than the critical Reynolds number, that is the turbulent flow. Okay, so R critical number less than Reynolds number. So this is the laminar flow, and this is the turbulent flow. So by finding the Reynolds number, you can identify the type of the flow. Okay, so we'll see. So next next layer is the thermal boundary layers. It means two types of layers we can observe. One is the velocity boundary layer, another one is the thermal boundary layer. So here we'll see thermal boundary layer. So it is the solid surface. So flow is like this one. So the water flows or some fluid flows on the solid surface. The just like so the fluid which is flows on the solid surface takes the heat from the solid surface. Automatically temperature will be decreases. Initially temperature high, and the temperature gradually decreases. So okay, at particular height, at particular point, this temperature increasing decreasing temperature very equal to the temperature very reaches very near to this steam temperature. It means fluid temperature. So it means that is the value is 99% of atmospheric or fluid temperature. So not equal, but very near to that value. So we can take that one. So T minus Ts by T infinity minus Ts is equal to 0.99. Okay, so by this formula. So it means, so at this point, this decreasing temperature, like this temperature initially high temperature. So the temperature, because this is the solid surface, high temperature body. So when the temperature takes by fluid, the temperature profile is decreases at one particular point. So that point, so this temperature, this T is very near to reaches very near to 99% of the just like steam temperature, that is at T infinity. So the point, so the distance from the solid surface to that point, that is called thermal boundary layer thickness. Okay, thermal boundary layer thickness, that is represented by delta T. So this is called thermal boundary layer thickness. So velocity boundary layer thickness, that is represented by delta, and the thermal boundary layer thickness, that is represented by delta T. Okay, so there is a relationship between them. So the relationship is shown by the Prandtl number. You know that. So it means del by delta T is equal to so Prandtl to the power of 1 by 3. So this is the relationship. Okay. So we can identify the Prandtl number by using the thickness of the boundary layers, velocity boundary layer and thermal boundary layers. Okay. So we'll see here. So delta is the velocity boundary layer, hydrodynamic boundary layer. Delta T is the thermal boundary layer. So the ratio between the velocity and the thermal boundary layer is equal to Prandtl to the power of 1 by 3. Okay. So you know that Prandtl number is nothing but molecular diffusivity of momentum by molecular diffusivity of heat. It is related to momentum, it is related to heat, it is related to velocity, it is related to temperature. Okay. Here just like showing the so Prandtl values. If the Prandtl value is greater than 1, so what is the diagram? So what is the just like relationship between the velocity thermal layer boundary layer thickness and the thermal boundary layer thickness. Okay. Here you can observe if the Prandtl number is greater than, so it means you know that Prandtl number is equal to del by delta T is equal to PR to the power of 1 by 3. So it means Prandtl number is greater than 1 means delta is greater than the delta t. It means velocity profile. So that is the delta is greater than the thermal boundary layer. So this is the thermal boundary layer, delta t. So okay, so next condition is the Prandtl number is less than 1. Prandtl number is less than 1 means delta t, the thickness of the thermal boundary layer, is greater than the thickness of the velocity boundary layer. It means this thermal boundary layer, delta t is greater than the delta. It means delta t covers the velocity boundary layer. So it means thermal boundary layer covers the velocity boundary layer. Here velocity boundary layers cover the thermal boundary layer. We'll see there's some matter regarding this one here. Already just I have pasted on this PPT. You can observe that one. So this one. So for the low Prandtl number, it means Prandtl number is less than 1. So that means liquid. So though Prandtl number fluids means example is equal to liquid and metals, liquid metal. So okay, here heat diffuses much faster than the momentum flow. Okay, heat diffuses much faster than the momentum heat flow. Okay, you know the Prandtl number is equal to mu by diffusivity alpha. So here here the velocity boundary layer, it means here the low Prandtl number. Low Prandtl number means this one. Okay. So here the velocity boundary layer, this is the velocity boundary layer, is fully contained within the thermal boundary layer. So it means this velocity boundary layer is covered by the thermal boundary layer. It means thermal boundary layer covers the velocity boundary layer. So in case of low Prandtl fluids, just like liquids and something, for high Prandtl numbers, it means Prandtl number greater than 1, like oils and something. Okay. So for this one, so heat diffuses much slower than the momentum. It means thermal boundary layer. So this is the thermal boundary layer. So this thermal boundary layer is completely covered by velocity boundary layer. So this thermal boundary layer is contained within the velocity boundary layer. So how to identify this type of relationship by the help of the Prandtl values. Okay, so you know that Prandtl value is nothing but so velocity boundary layer thickness by thermal boundary layer thickness. You have to remember this one. Okay, so next one is the Nusselt number, because just I'm explaining, already explained about the Reynolds number and Prandtl number, and now just I'm explaining Nusselt number, because so these three numbers are very important to find the H value for the forced convection, because to find H value, it is depend upon the Reynolds number, Prandtl number, Nusselt number, because you know that Nusselt value, so it is the dimensionless temperature gradient at the surface. You know the all these numbers already learned according to dimension analysis, which are covered in fluid mechanics. Okay, I think no need to explain about that one. You know the formula Nusselt number is equal to Q convection by Q convection. Okay, so you know the formulas for the Q convection. Convection is equal to HA delta T by so Q convection, so Ka delta T by L. Okay, area cancel, so the L comes top, HL delta T cancel, HL by K. So this is the formula, HL by K. So H is the rate of heat transfer coefficient, K is the thermal conductivity, L is the length of the solid surface. Okay, so by using this formula, you can find out the H. For finding H, you have to know about the Nusselt value. But Nusselt value have some formulas which are related to, which are based upon the Reynolds number and Prandtl number. So we'll see that one also. So you know that so these formula, so it is very important. Nusselt is equal to HL by K. You know the formula. This is nothing but capital C into Reynolds number to the power of m into Prandtl number to the power of n. So this C comma m comma n is these are the constants. So uh, so this depend upon the type of the flow or type of the solid medium. Either it is solid surface, either it is just like a hollow pipe or anything. So these parameters depend upon the solid geometrical structure of this surfaces. Okay, so this formula, has been derived by the help of the, by solving the conservation of mass and the momentum and the energy equations. Here I am not explaining the so loss of conservation of mass and the momentum for the fluids and the energy equation for the fluids. I am not deriving this one. Just I am writing directly. I am taking the formulas which are derived by solving these equations. Just I am writing formula directly. So by solving those equations, you will get this one Nusselt relation, Nusselt value with the relationship of Reynolds number and Prandtl number. Okay. So finally, Nusselt value is equal to, so Nusselt formula, you know that based upon the conduction and convection. So that is equal to C into Reynolds number to the power of m into PR to the power of n. So C and m and n, so depend upon the geometrical structure of the surfaces. Okay. Next, to solve this one, H values and Reynolds values and the Prandtl values, so all these values, you should require the properties of the fluid, particular fluid. So to take or to identify those properties, how to take the T mean. So film temperature we have to find out. So film temperature is nothing but Ts plus T alpha T infinity by 2. It means temperature of the solid surface plus ambient temperature by 2. By using this ratio or average of this one, so you will find that film temperature. By using the film temperature with respect to the temperature of that fluid, particular fluid, we can take the properties, okay, with respect to the fluid. When you solving numericals, you can understand clearly. Okay, we'll see. So types of Nusselt formulas based upon the flow type, laminar and fluid, turbulent, and because Nusselt formula is depend upon the type of flow and geometrical structure. So it means flow over the flat plate, flow through the just like circular pipes. Okay, so based upon those flows through some solid structures, the C and M and N values will be changed. You'll see some formulas, standard formulas. So first of all, I'm just explaining the laminar flow. So if it is the laminar flow, so this is the formula for the Nusselt value. Here also two types of formulas are given. So at a trailing edge and a trailing end, it means so at x is equal to 0, at x is equal to L conditions. You can say, so this is the for like, this one is the average Nusselt value. It means so Nusselt value at full length of the plate. Okay. So first of all, you'll see the at x is equal to some value, a particular distance x, Nusselt value of that fluid. Okay, you will find that one. So here Nusselt at x is equal to h x by k. Okay, so it means particular distance or throughout the surface you can take. So that is HL by k. It is hx by k. So at particular distance. That is the formula is equal to 0.33 into RA to the power of 1 by 2 PR to the power of 1 by 3. So how to remember these formulas. So you know that type of flow is identified by the Reynolds number. You know the formula for the Reynolds number. Rx is equal to just like U alpha x by mu, or rho U x by mu also. So by using this Reynolds number, if the value is less than the critical value of the Reynolds number, then that is laminar flow. If that value is greater than the critical Reynolds number, that is the turbulent flow. So based upon the Reynolds value, you can identify type of flow, either it is laminar flow or turbulent flow. For the laminar flow, you have to take this formula. Okay, so Cfx is the just like drag force, coefficient of the drag force. Cfx is equal to 0.664 by under root of the Reynolds number. So you have to remember these formulas. So it means these two formulas always depend upon the type of flow, either laminar and turbulent, and the geometrical structure of the solid surface. You have to remember these formulas. Next, here, just like second one is the, so initially x is taken some value. So now x is equal to L condition. It means at the end of the solid surface, this is the formula. So the average coefficient friction and Nusselt number, average Nusselt number, you can call it. Average means at the end of the solid surface. Okay, so Nusselt number over the entire isothermal plate. So that is the Nusselt is equal to HL by K. That is the formula. So that is the previous one is equal to 0.33. So here is equal to 0.664. Previous one is equal to 0.332. So it means it is double for this one. So it means 0.664 RE to the power of 1 by 2 PR to the power of 1 by 3. Same formula. Okay. It means previous one is a 2 into 0.332 RE to the power of 1 by 2 PR to the power of 1 by 3. So double of that one. Okay. So similarly, so for the multiplication of with 2, so this is the 1.328 under root REL. So this is the formula. This is the formula for drag force coefficient, Nusselt formula. Right? So you know that for this solid surface, just like critical Reynolds number value. Critical Reynolds number value is equal to 5 into 10 to the power of 5. You have to remember this one. Okay. So for the just like outer flowing, it means flowing of fluid on the solid surfaces. For the inner fluid is just like flowing in some hollow tubes and hollow cylinders. The Reynolds value is different, but here is Reynolds value is different. You have to remember that one. Okay. So Reynolds value is also depend upon the type of geometrical structure of the surfaces. Okay. Now we'll see the turbulent flow. You know that one. Turbulent flow. It means the Reynolds value is greater than the 5 into 10 to the power of 5. If the value of the Reynolds is greater than the 5 into 10 to the 5. So you can identify that. You can take that one turbulent flow. Okay. So this is the formula for the turbulent flow. Here also two conditions. One is x is equal to at x value at L value. Okay. So it means Nusselt with respect to some x distance, h x by k is equal to 0.0296 into RA to the power of 4 by 5 PR to the power of 1 by 5. So these equations came from the solving of just like momentum and just those values already explained in previous one. So I have to remember this one. So Nusselt value is equal to hx by k. So that is the 0.0296 into RA to the power of 4 by 5 PR to the power of 1 by 3. Okay. So here condition is equal to Reynolds value is equal to greater than the 5 into 10 to the power of 5 and less than 10 to the power of 9. Okay. So this is the coefficient of friction. That one is the 0.0592 by Reynolds value. So all these values uh, we can take from the data book also. We can use the data book and we can solve the numericals with the help of the data books. Okay, so this is the formula for the turbulent flow. It means in laminar flow, two conditions is there at x and x at L. Take the Nusselt values. Nusselt with respect to x, Nusselt of value of x with respect to L. It means end of the solid surface. Here also for the turbulent, two fluid formulas are there at particular x and x is equal to L. It means at L. Here formula is equal to L. So that is the average frictional coefficient, Nusselt number over the isothermal plate. It means so Nusselt is equal to HL by K. So double up this one 0.037 RE to the power of 4 by 5 PR to the power of 5 4 by 5. If you remember anyone, just automatically you can multiply this one with 2. So that is the value. So CFX, coefficient of friction, is equal to 0.074 into under root. So RE to the power of 1 by 5. You have to remember this one, not under root. RE to the power of 1 by 5. So these are the formulas. So by using these formulas, we can solve numericals in next class. Thank you for watching this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.